this video I want to introduce to you likwid-pin. Likwid-pin allows you to pin processes and threads to specific cores. It directly supports pthreads and openmp. No code changes are required to use it. It supports logical IDs within topological entities. To use it, your binary needs to be dynamically linked. Likwid is designed for pinning to dedicated resources. Other strategies for managing thread affinity are not directly supported. To understand the following material, we first need to introduce some terms and concepts. An application process or thread is an instruction stream. An instruction stream is a sequence of machine instructions. In an operating system context, this instruction stream gets executed on a processor. You could say that a processor is a hardware entity that can consume a single instruction stream. Unfortunately, the term processor has a different meaning in other contexts. Hardware vendors or the computer architecture community use the term processor for a package or a whole chip, so something you buy. To prevent a misunderstanding of the term processor, we will use the term hardware thread instead. While a hardware thread is an abstract receiver of an instruction stream, on a real hardware design you need execution units that can execute the instructions. Multiple execution units are organized in a core. Here you see a very simplified example for a core having a floating point unit, a general purpose arithmetic logical unit, and a load store unit, and a two-level private cache hierarchy. There are modern core designs which offer two or more hardware threads simultaneously and can execute multiple instruction streams at the same time. Of course, most of the core resources are still shared. This is done to increase the average utilization of execution resources within a core. In an operating system context, hundreds, if not thousands of processes or threads are running. Because only a very limited number of hardware threads that can consume instruction streams are available, the question arises, who manages the distribution of available compute resources on threads and processes? This is a central task of an operating system, and the component who does it is the task scheduler. Now, if the operating system manages the distribution of resources on threads and processes, why do you need another tool? To illustrate different cases, I have prepared a simplified example. We have a socket with 4 cores where every core exposes 2 hardware threads. The hardware threads are numbered by the operating system. While the numbering usually is not as random and arbitrary as in this example, it is not standardized and can be arbitrary. We also refer to this operating system numbering as physical IDs. In our example, we have an application with 4 threads. The operating system might decide to put the first thread on the first hardware thread of the first core and the second thread on the second hardware thread of the same core, and the 2 threads that are left both on one hardware thread of the third core. After a while, a reschedule might happen. This means that the operating system reconsiders the scheduling and puts, for example, one of the threads on the third core on the second hardware thread of the fourth core. This already illustrates 2 reasons why pinning is important, especially for benchmarking. Those different cases, for example, 2 threads running on 2 hardware threads of the same core, or a thread running on a hardware thread and having the core on its own, or even worse, having 2 threads scheduled to the same hardware thread of a core makes a huge difference in performance. All this causes that on multiple runs you could get a large variation in benchmark results, making it very difficult to have reproducible and consistent results. So a possible contention on hardware threads and cores is the first reason why you should care for affinity control. The second reason is thread migration that may occur. As you have seen, the scheduler might decide to put the thread on another hardware thread. Of course, this causes again warming up the cache hierarchy, which costs a penalty. To wrap it up, to let the scheduler of the operating system decide where the threads are running on a massively parallel system with an application with a lot of threads is not an option. For benchmarking especially, you want to have full control. You want to deliberately decide where your threads are running. For example, you may want that every thread has its dedicated core on its own. Up to now we were talking about contention on execution resources, but the same applies for the memory bandwidth. Here is an example of an older Intel Xeon architecture generation around Haswell and Broadwell. Those architectures had originally 4 memory channels per memory interface and 1 memory interface per socket. But there was a BIOS option where you could enable a special mode called cluster on die mode. In this mode, the memory interfaces were cut in 2, so creating 4 memory interfaces and 4 memory domains with 2 channels each. This results in a better bandwidth and better latency behavior. Because also the bandwidth is generated through parallelism, also here the affinity is key to get the best performance. Again, it makes a very large difference if you put all threads in one memory domain, like in this example, or if you distribute the threads across all memory domains. In the first case, you potentially only get a fraction of the overall memory bandwidth. The task scheduler has a so-called CPU affinity mask for every process or thread. The CPU affinity mask is a bit set where every bit represents one hardware thread. Only the hardware threads where the bit is set is considered for scheduling. The CPU affinity mask can be configured using the scat-set-affinity Linux system call. If only one bit is set, the thread can run only on one hardware thread. This is how pinning is implemented. likwid-pin is used as a wrapper to your application. In the simplest case, you just provide a list of physical IDs to determine where the threads are running. The real benefit of using likwid-pin comes by using the logical numberings. For this, we need to introduce some liquid terminology and syntax. Liquid has so-called thread domains. A thread domain is a topological entity that is shared by a certain number of hardware threads. A thread domain is defined by a single character plus an index. For example here, S0 stands for socket 0. A thread group is then a number of threads that run within a thread domain. A thread group expression can consist of ranges or lists of IDs. Multiple thread group expressions may be chained using the add character. A thread group expression specifies the mapping of the threads to hardware threads using logical numberings within the thread domain. Here you see an example where 4 threads are pinned to dedicated cores. As you can see, if you use the thread group syntax, the numbering is physical cores first. So in this example, with 4 cores, the IDs 0 to 3 is the first hardware thread of each core, so the physical core, and the IDs 4 to 7 are then the second hardware thread on the cores. To illustrate which thread domains are currently supported, we look at an artificial node architecture. So this node consists of 2 sockets. Every socket has 2 dies with a memory channel each. Within the die, there are 2 cores having 2 SMT threads each, with 2 cores sharing a last level cache. The first thread domain is the complete node. This is the default if you don't specify any command line argument to likwid-pin. Next is S for socket, M for memory domain, and C for outer level cache group. The beauty of this syntax is that if a new topology exists, we can just add another character without breaking the basic syntax. Liquid supports also an alternative syntax, which is called the expression syntax. The expression syntax generates a thread group from a number of threads within a thread domain. So you don't have an explicit list, but the list is generated. In contrast to the thread group syntax, the expression syntax uses compact placement. So the threads are consecutively placed to adjacent hardware threads. To use the expression syntax, you have to start with an E for expression syntax, then a colon, then you specify the thread domain, here in this example, again, socket 0, another colon, and the number of threads you want to use. That's the required part. There is an optional part, where after another colon you specify the chunk size and an optional stride. The expression syntax is, for example, useful if you want to use a subset of hardware threads on a subset of cores. This is very difficult to do in the thread group syntax if you have a large number of cores. It may also be more convenient to use in, for example, benchmarking scripts where you just specify the number of threads to use. Here you see the previous example, but now using the expression syntax. If you want to use just the physical cores, so only the first hardware thread on each core, you have to provide a chunk size on stride. So in this example, the chunk size is 1, and then the stride, so the distance between two threads, is 2. I want to show you the usage of likwid-pin in a small demo. In this demo, I will use a benchmark that is available on our GitHub account. This benchmark is called the bandwidth benchmark. It is inspired by McAlpin's stream benchmark and contains a collection of streaming kernels. If you're interested in this benchmark, I will put the link in the info box. The first thing you should try is the -h command line option. This will output the supported command line options and some detailed examples how to use likwid-pin. Usually, we only need the -c command line option. Other useful options are the -p option that prints all available thread domains and the -q option that suppresses the output. Lesser known options are the -i command line option that enables interleaved page placement on a NUMA system, and the -S option that will sweep memory and last level cache to have a clean state before benchmarking. Before pinning, it is recommended to call liquid topology to see how the node looks like. In this demo, we're using an Intel Broadwell-based system with cluster on die mode enabled, so as you can see, the system has 4 NUMA domains. The bandwidth benchmark is threaded using openmp, and the first thing we want to try is to just call it without any other settings. As you can see, per default, as many threads as there are hardware threads in the system, so on the node, are used. In this case, 72 threads. As you can see, the benchmark outputs the result for the various different streaming kernels. For the sake of this demo, we will look on one specific case, that is the triad kernel. The first thing we want to try is to use likwid-pin to run the bandwidth benchmark in sequential mode, so only using one thread. As mentioned, one advantage of using likwid-pin is that the pinning expression also implicitly sets the number of threads, so sets the environment variable ompnum threads in case of an openmp threaded application. We use here logical pinning, so we pin the one thread or the process to core 0 on socket 0. The likwid-pin output is in blue here, so as you can see, when you start your application, initially at the start the process is pinned, and that's it in this case, and then comes the output of your program. Please be aware that the likwid-pin output always uses physical hardware thread IDs. So here core 0 is really also the processor 0 in the operating system context. The bandwidth benchmark also outputs the number of threads used here. If your application does not output the number of threads, this is another benefit because likwid-pin outputs or gives you some feedback how many threads are used. So in this demo, the actual performance number is not important, so I will not discuss why the performance is how it is or why different kernels show different performance numbers, in this case bandwidths. This is the topic of another video, but still let's remember for the moment that with one thread we get around 9 GB bandwidth. So let's assume that we want to see how well the bandwidth scales within a memory domain. For this purpose, the socket domain is not the correct one because here on this architecture, one socket actually has 2 memory domains. So the correct thread domain we want to use is capital M for memory domain. For the sake of completeness, just repeat this with M0, 0. Of course, we now expect this to show the same pinning behavior and the same performance. So the output is, as expected, identical to the one using socket 0. So now let's scale out and do the second run with using 2 threads. So M0 with the thread expression 0 to 1. Now the output changes a bit. You have now the process main is pinned to core 0, and then the first thread is pinned to core 1. If you ask yourself what this skip mask is all about, this is in cases where the runtime uses a thread for itself. You don't want to pin this thread, and therefore there's the skip mask, which indicates that some of the created threads are not pinned, so are skipped. So now we can just go on and use 4 threads, so M0 and then thread expression 0, 2, 3. As you can see, again for our triad kernel, there is some scalability, but it's not perfect. So we get some increase in performance when using more threads, but it's not linear. So next, using now 6 threads from 0 to 5, and as you can see, the memory bandwidth of the triad kernel actually does not scale much more. So it seems to be reaching saturation. So finally, using all physical cores in the memory domain, so 9 cores, and again, as you can see, the triad bandwidth is in saturation, so you don't get better performance when using more threads, in this case for this memory bandwidth limited kernel. Now to demonstrate the round drop-in feature of the thread expression syntax, we just now use index 0 to 9. And as you can see in the output, the first 9 threads are from 0 to core 8. And then the 9th thread is on core 36. If you remember the output of liquid topology, you know that the SMT threads, or the hardware threads, the second hardware thread is numbered round robin, so the second hardware thread of the first core has the ID 36. This means that now 2 threads are running on the first core, whereas all the other threads have their dedicated core. Of course, this is not ideal for performance because those 2 threads compete for resources, and therefore, as you can see, the performance slightly decreased to around 20-21 gigabytes per second. Now, let's see what happens if you actually specify ompnum threads in your environment. So we're using env and set ompnum threads equals 4, but we don't touch the rest of this thread expression. And as you can see, likwid-pin will acknowledge that ompnum threads is already set and will use as many threads as are specified with ompnum threads. So in this case, 4 threads. You may use this way to also scale out. You set a fixed pinning expression and you just increase the ompnum threads variable. That's also an option. Now let's check out some useful options. And the first option that is quite interesting is likwidpin-p. This prints out all available thread domains and the physical hardware thread IDs that belong to each of those thread domains. And as you can see, as we already discussed on this architecture, the memory domains are equivalent to the last level cache domains, but are not equivalent to the socket domains. So there are 2 memory domains per socket domain. So next, just run the benchmark using all physical cores on the node. So specify the capital N for node, and then the IDs 0 to 36. So as you can see, because there is 1 line per thread output from likwid-pin, this is quite a bunch of output. And because this output occurs when you enter the first parallel region in your code, it might happen that the other output of your program that was before this first parallel region scrolls out of the terminal window. While it's nice to have some feedback, how many threads are actually running, for benchmarking, maybe you don't want to fill up your output with likwid-pin messages. And for this, there is the option -q. -q suppresses all likwid-pin output, as you can see here. So next we want to use 2 memory domains, and for the sake of this demo, we want to use 2 memory domains that are not on the same socket. And you can use this with the add symbol. So here, for example, we're using 6 threads on memory domain 0 and another 6 threads on memory domain 2, which is located on the other socket. That was it for the thread groups syntax, and next I want to show you some examples using the expression-based syntax. The expression-based syntax is indicated by a capital E at the beginning, and then you have 2 required parameters. The first is the thread domain in which you want to place the threads, in this case the memory domain 0, and then the number of threads you want to use, so in this case 4. As you can see at the output, this is the major difference between the 2 syntax forms. In this case here, using the expression-based syntax, the pinning is compact. So as you can see, the threads are placed consecutive on the hardware threads. So the process runs on core 0, and then the first thread runs on the second hardware thread of core 0, so core 36. This is actually a bit disturbing that that in the output they are all called cores. And the same for the last 2 threads. So they're running consecutively on core 1. This means if you want to use physical cores only, so only run 1 thread per core, you have to specify 2 additional parameters to the expression syntax. And this is the chunk size and the offset. So on typical Intel or AMD processors, which usually have 2 hardware threads per physical core, you need 1 as chunk size and 2 as offset to only use 1 thread per physical core. And as you can see, using this expression produces the same output as using the thread group syntax. So the 4 threads run on 4 dedicated cores. Of course, you can also chain the expression-based syntax, so the same rules apply as for the thread group syntax. So last, I want to show you a not that well-known option, and this is the -S option. This option is useful for benchmarking if you want to initialize the memory hierarchy in a well-defined clean state. So it, so to say, cleans the last level cache. Depending on the size of your last level cache, this might take some time, but it's worth to give it a try. When you have a benchmark that is sensitive to cache performance, it might give a difference in performance. I hope this video was useful to you. If you have any questions, you can contact us at the Liquid user mailing list. You can find the contact information in the info box.